Alright guys, so today we're going to look at compound sentences and truth tables a little more. And we're going to talk about logical expressions. So a logical expression is an expression in which variables representing statements are combined using and, or, not, or, if then. Okay. Now, some examples would be not P and Q, okay? Or we could have something like not P, and then we would do or Q. Okay, not P and Q. So if you saw that written somewhere, this is not a logical expression because it is not clear whether it means not P and Q or if it means not P and Q. All right, so what we're going to do is we're going to do a little truth table, okay? So what I'm going to do is right here, this is going to divvy up the two problems. Okay, so we're going to do this problem over here and this problem over here. Okay, but we're only going to do P and Q one time. So we have P, Q. Remember that P and Q is always true, 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 false, false, true, false, false. Okay? Now, we're going to work in parentheses first because order of operations still matters. So we're going to do P and Q. Okay, remember for P and Q, what has to happen for and? Okay, we learned this before. Both have to be true. So we're looking at these. So P and Q, both of them have to be true. So the only one that's true is this first one. Okay. Now what are we supposed to do to it? So the next thing we're supposed to do is not P and Q. So we're going to not this row because this is the P and Q row. Okay. So we're just going and we're going to not these. So what not does is it makes it the opposite value because that's what we learned with negations. Okay. So I'm going to put a little note right here that says opposite. So this is going to be false, true, true, false. Okay. So we're going to compare this problem to this problem. Notice the difference. This says P and Q, then you're going to not it. This one says not P, not Q, and then you're going to have an or. Okay, so we have the P and Q here. So we're going to do our parentheses first. So we're going to do a not P here. We're going to do a not Q here. Okay, then we put them together and do an or. So not P or not Q. Okay, so let's talk about what this means we're going to be doing. So here, not P means opposite. So go to P and we're going to put the opposite. So that's false, false, true, true. Okay, so not Q we're also going to do the opposite. Okay, so go to Q and put the opposite. So false, true, false, true. Now, remember for not P or Q, the or means one or both can be true. Okay? So as long as there's a T somewhere, and we're comparing this row and this row, the not P's and the not Q's. So are there any trues here? No. So that's a false. Are there any trues here? Yes. So that's a true. Are there any trues here? Yes, that's a true. Are there any trues here? Yes, that's a true. Now, the question are, do any of these two columns have the same truth value? So if we look here, no, nothing has that. Oh, look, right here. So watch what happened here. When you do a not, it distributes to each piece, and when you not an and, it becomes an or. So it's kind of like distributive property. Okay? So you have not P and Q and not P or not Q have the same truth value. So they are logically equivalent. Okay? And the symbol for logically equivalent is like an equals, but it means a little more. So you add a third line. So it's 3 lines. It's like an equals with a third line. This means logically equivalent. Okay. Now let's look at this in terms of Venn diagrams. You know how we did that in the previous lesson. So we have not P and Q. Okay? So P and Q is right here. So it's not that. Okay? So let's label these P and Q. P and Q. P and Q. P and Q. And if you need to pause, oops, you need to pause and draw these 4 Venn diagrams, feel free to do that. So, all right, so not P and Q. So this part right here is P and Q. So it's not that. So it's everything but that. So it could be in here, and it could be all out in here, just as long as it's not in here. Okay, let's look at the other problem. The not P. So if it has anything to do with P, so anything to do with this circle, it can't be that. So it could be that or anything out here. Okay. Then we could do not Q. So that would be anything but the circle that has Q. Okay. So not P or not Q would again be everything but the overlap when you put them together. So what they have in common that's not colored is the overlap. Okay? Now remember that the squiggle line means not. So De Morgan's law, give me just 1 minute to scoop this up. De Morgan's law says for all statements P and Q, if I have a not on a P and Q, that is logically equivalent to doing distributive property, and it changes the sign on everything, and it changes N to an OR. So it goes not P or not Q. And if I were to do that with an OR statement, I want you to think about what you think it will happen there. If you said not P and not Q, you would be correct. And that means that they are logically equivalent to each other. Okay? And the lines are supposed to be the same length. I'm just not great at always making them the same length. All right, so let's go to the next page. These laws provide the basis for negating statements with and or. Okay, so changing and to or. I'm going to put in parentheses here vice versa, which means changing or to and negating each component of the statement. All right. Example 3. At a movie theater, there are 2 admission prices, depending on an age in years of the patron. A regular price for a patron for which the age is between 12 and 60, the discounted price for everyone else. Okay, so if you're between 12 and 60, you pay the regular price, and it's discounted if you're below 12 and above 60. Okay, so we're going to use De Morgan's Law to describe the patrons who get a discount. So the people who do not get a discount are the people that are younger than 12 and the people that are older than 60. Those are the people who do not get a discount. So we're trying to figure out the people who do get a discount. Okay, so we're using De Morgan's laws. So we're going to do not these people. Okay, so what does that mean? Well, we're going to negate this, and change this to or. Okay, so when you negate this, remember it flips the symbol and you get the equal to if it wasn't there. Oh, wait a minute. I wrote that wrong. You're probably sitting there yelling at me. The people that are older, I was doing the people who get a discount. So the people greater than 12 and less than 60. All right. I was like, that doesn't make sense. I was writing the discounted ones. Okay. So, who doesn't get a discount? Those people. If you're older than 12 and less than 60, you don't get a discount. So now we're going to do the discounted. So anybody less than or equal to 12 or anybody greater than or equal to 60. Okay. So patrons 12 and under or 60 and over get a discount. Sorry about the mistake on that, guys. All right. Next, use De Morgan's Law to simplify the negation of the statement. All good movies must have a great storyline or great special effects. Okay? So, the given is for all good movies M. M has a great storyline or M has great special effects. So, there exists a good movie. This says does not have a great storyline and does not have special effects because you negate this, and this becomes and. So, all you have to write is the following. Simplify this negation. So you're going to go, some movies some good movies, let's put that, some good movies don't have a great storyline or great special effects. Oh, and great special effects. I'm looking at the wrong word. Okay. Some good movies don't have great storyline and great special effects. All right. And that's it for today. Thank you, guys.